So he'll be talking about, can I see the title? Born-Oppenheimer Effective Theory for Multiquark XYZ Hadrons. Yeah, you can start now.
Okay. So everybody can hear me, yes? Good.
Yeah, we can hear.
Yes. Okay, thank you. So thank you for the invitation. I will be talking about the effective theory for the multiquark XYZ hadrons. We see XYZ hadrons for past 20 years or past 2 decades. We have been seeing these XYZ hadrons in the experiments, and with more and more upgrades, we will see more and more new XYZ states in the coming future. So this work or the presentation will be based on the three questions. This would be a long paper and the follow-up of the 2 applications of this long paper. So before I delve into the presentation, I just want to give a brief background of the topic that I have addressed in my research, like current and the past. So my presentation will be on the XYZ mesons. I have, I have, I will talk about the spectroscopy and the decay part. And this is the focus of my research during my postdoc. In my PhD, I have worked on axion dark matter, non-relativistic axions, and axion stars. And the focus of my work was on studying gravitationally bound configurations of axions. Basically, I developed axion EFT framework and studied signatures of axion stars. Maybe let me close this window here. And then another system that I had contributed in my PhD during my PhD was emergent symmetries in ultracold atomic gases, where I studied three-body bound states like Efimov physics and connection with loss of conformal symmetry using zero-range electricity. My talk will focus on the first part, which is the XYZ mesons, basically. Okay, uh, so as we know, the QCD spectrum only consists of color singlet states that exist, that we call as the hadrons that exist in nature. And until 2003, all the hadrons were either classified as mesons or baryons. So example of meson is a pion here, and a baryon is like the proton, the simplest example. But things changed after 2003 when the XYZ mesons were discovered. And the first XYZ meson that was discovered was this X3872. We now call it as Chi-C13872 as per the new prescription. And this was discovered by Bell. So I will touch upon how we describe this state in the Born-Oppenheimer effective theory. So the talk will focus on the non-relativistic bound states of two heavy quarks. The heavy quarks are charm or bottom. We do not focus on top at present because top has a very short lifetime. And given the lifetime, it won't form these XYZ mesons as a stable states. So we will only focus on charm or bottom. However, I want to highlight that recently LHC did indicate something about toponium states, which are bound states of TT bar. So here is the spectrum of exotic XYZ mesons in the charm sector. In the blue color is the conventional quarkonium states. And in the red are all the exotic states that we do not know how to understand their pattern. We know how to understand quarkonium's pattern, but we do not know how to understand the XYZ pattern. And if you do a recent count, so this plot is slightly bit old. It's around 2020. There are more number of states that have been seen. The plot has not been updated. But I gave a recent count here. In total, there are around 60 XYZ mesons that has been seen in the charm sector, mostly in the charm sector, couple of them in the bottom sector. And there are states where the exotic states is made of, where the exotic state is made of all charm quarks. And in last 2 years or 3 years ago, there was this famous exotic.
Hello, I have a question. So are these all experimental results you're showing?
Yeah, these are experimental results currently.
Okay, and are all these excited states are all having like 5 sigma discovery, or these are all?
Yeah, these are all either have 5 sigma or even 7 sigma.
Okay.
Yeah, I mean there are pentaquark states which has been seen at 8 sigma discovery. I mean they have been confirmed. So these are all states that has been confirmed by multiple experiments. They have been all observed at 5 sigma.
And when you say that the pattern is not known, what do you mean by that?
I mean, we do not know. We see them in experiments, but theoretically, nobody can tell you how to explain the pattern of these states, how to get to the quantum number, what new exotic states that I can see in the future. We do not know. Nobody can tell you. So that's the question. Or nobody can explain why certain exotic states are lying close to threshold, why some are far away from threshold, why some are molecules, why some is like a compact state. There is no answer to it right now. In
But
in simple in simple sense, for example, I take quarkonium. I can solve my Schrodinger equation with a Cornell potential. I can predict my states, where the quarkonium states with what quantum numbers can come up. But XYZ mesons, there is no clarity on them.
okay, yeah.
So So as I mentioned, with new experiments, more exotic mesons will be seen. We do not know what the masses are. We do not know what quantum numbers are. Even some of the exotic states, we do not. Here I'm showing some of the states where the quantum number is well known. There are some states, as you see on the most right-hand side, there are quantum numbers are even not known. So it is the golden age of hadron spectroscopy to focus on. Actually, this can
Uh,
tell a lot about QCD.
but I have, sorry, I just to ask. So these are all either four body states or three body states, and we know that those potentials are not very well known, right?
Yes,
So is it a surprise that we do not know the excited states of this?
I mean
Because
it
the
is.
Cornell potential, we know it is a two body bound state. You
Yes,
approximate it with the Cornell potential, though we know that there are several other correction terms we calculate
yes,
from effective field. They just Cornell
yes.
potential doesn't help.
Yeah,
But
yeah. I
in
mean there are
these cases, of course, it is not surprising because you may have three body terms, four body interactions,
exactly. This is
and those
exactly.
are extremely difficult to solve in nuclear physics also, right?
This is exactly I will touch upon. I will show you new results based on the tetraquark potentials predicted from Born-Oppenheimer EFT. So we have done a breakthrough in Born-Oppenheimer EFT and starting to now focus on understanding the pattern, I would say.
Okay.
I will show you results on tetraquark, pentaquark for some of the states, but obviously there are many states that has to be still addressed. So this will I will touch upon it.
Okay. So my point was that getting a pattern is always very difficult in these kind of potentials. So we should
Yes,
not a priori expect that,
no,
right?
but for
Suppose
20
in
years.
atomic physics, in molecules and all, we don't expect like a pattern states or something like that.
And the point is, experiments look for these. I mean, first of all, they do some collision experiments and they find a state out. Nobody understands that whether this state is a mixture of four states. It can be a tetraquark state. It can be a mixture of hybrid tetraquark. It can be a mixture of hybrid quarkonium and tetraquark. Nobody understands how to explain these states at all.
Yeah,
So
sure.
this is the problem. I mean, people focus, or I will mention, people focus on specific model. Every state cannot be a molecule. Every state cannot be a compact thing. States which are close to threshold will be molecules. States which are far away from threshold could be compact. But molecular models or compact models, they assume every state is compact, every state is a molecule, which is not correct.
Yeah. Yeah. Please go ahead.
Okay, thank you. So I hope this is not blocking. I'm sorry. Okay, so let me just minimize. So there are these models that has been for past 20 years people has been using to study them. Like I told, people assume specific models and with specific interaction that have no real connection to QCD. They add some term to explain the configurations of the state. But the problem is, like I mentioned, some states are close to threshold. Like the example is Chi C13872. Again, I will touch upon it in the future in the upcoming slide. And some states are far away from thresholds. For example, the state is like a side 540 to 30 or something. And so a model at some point I mean, they have some limitations. So the question is there is a comprehensive framework that can one build starting from the first principle of QCD, use ab initio methods, and describe these all XYZ hadrons. I break down in two parts here, which is the hybrid on tetraquark and pentaquark. The reason being, for hybrids, first of all, the hybrids are quark antiquark with a gluon, excited gluon. These are isospin scalar exotic states. And for hybrids, there are multiple lattice results that has been available in the literature. For tetraquark and pentaquark, there are no calculations available. There are new theoretical predictions that I will tell you that I predicted based on the Born-Oppenheimer EFT and symmetrical state. So tetraquark and pentaquark can be non-zero isospin states.
Sorry, why are you telling that there is no theoretical results? Because there are lattice results on this.
I am telling that they are for which case?
For the tetraquarks and pentaquarks.
There are no lattice results on the static energy. There are results on the spectrum, but there are not results on the potentials.
Yeah, potentials, we do not know. How will you define them? Like, for example,
Let me touch
yeah,
upon it.
let's see. Yeah, sure. Yeah.
So let me describe the principle of Born-Oppenheimer EFT. So I have an exotic hadron where I have a heavy quark, heavy anti-quark, and X is my light quark or gluons. It can be any number of light quark or gluons. It's just that it has to be a color singlet bound state. There are multiple scale in this exotic system. So starting with the heavy quark mass, then there is the energy scale lambda QCD, relative motion between the two heavy quark, which defines the relative momentum, and then there is the heavy quark binding energy. What we generally find is that for a state like exotic, the hierarchy of scale that satisfies is that the lambda QCD is greater than the binding energy. We indeed find it. And because of this hierarchy, one can immediately find that the time scale for the dynamics of the two heavy quark is much, much larger than the time scale for the dynamics of the light degrees of freedom. So heavy quarks can be considered to be static at first approximation with respect to the motion of the light quarks or gluon. And this is the famous Born-Oppenheimer approximation that is exploited in molecular systems to describe molecules.
But how well is it true for charm quarks?
It is quite good for describing the low-lying charm quark states. For excited states, obviously MV square starts to get lambda QCD scale. And at that point, you have to add mixing terms. You have to add higher order terms that can mix, for example, several states together.
Like we know from finite temperature that the charm cannot be, the spectral functions cannot be addressed within NRQCD.
Yeah, but for the spectrum, like I said, for the lowest charmonium hybrid, this hierarchy is satisfied. For state like Chi-C13872, which is a bound state of charm anti-charm with two light quarks, this criteria is satisfied. And like I said,
but never it is much greater than MV. M is not never much greater than MV. It may be a little bit order of
the V square for charmonium, if you take in bottomonium, is roughly about 1/3. So I mean, the criteria, the hierarchy is obviously well satisfied for the bottom. There is no absolutely doubt.
Yeah, that is true. Yeah, that is.
For charm quark, like I said, for the lowest charm quark, it is quite well satisfied. For excited charm quark, there is always a problem. I mean, for charm case, this is NRQCD always depends upon what observable you want to calculate. So, but like I said, for lowest charmonium states, whether you take J-psi, psi2s, or charmonium hybrids, or even X3872, this hierarchy is quite well satisfied. We explicit.
From the spectral function study, we know it is not from finite.
I mean, I'm not much aware of the finite temperature part. This is something.
No, even finite temperature before melting is almost similar to zero temperature physics. So there, we have to calculate the spectral function ab initio without going into NRQCD.
Yeah. Okay, let me just give you the numbers. For example, if you take, for example, J-psi, MV square is roughly around 50 MeV, which is coming from the kinetic energy part. Lambda QCD here is the hadronic scale for us. So it is roughly around 500 to 1 GeV. MV is sitting up somewhere around mass of charm. If you take about 1.5 and V square is 1/3, it is roughly around 900 orders. And M is obviously 1.5 J. These numbers come from J-psi. These numbers is similar in the case of charmonium hybrid, for example. MV square increases because the size increases a bit. So MV square is now in charmonium hybrid is roughly of order 150 to 200. Lambda QCD is again something around 500 to 1 JeV. MV is sitting around 900 and M is again 1.5. The same criteria is satisfied, at least in the spectral part. in the spectrum.
Yeah, but it is not much greater. So I think the
I mean, not
NRQCD statement.
so the not. I mean, I'm describing both charm and bottom here. Yes, okay.
For
In charm,
bottom, yes, I understand, but for
but
charm, it is a little bit. I
I'm not
would
saying.
not.
Yeah, I agree
Yeah.
with you that I'm not disagreeing with you that in the charm case it is one has not to be careful. Obviously, one has to be careful. But yes, I mean, in charm case, you can say M is greater than MB. MB is of order lambda QCD. Lambda QCD is greater than MB square. Not much greater. But for bottom case, it is definitely much greater.
Yeah.
We are
Also,
building.
this V equal to 1/3. That also is a little bit
I mean,
tricky for
somewhere
charm. This is also
V
tricky for charm.
you
Yeah.
derive it from V square is of order 1/3. You derive it from the thermonium spectrum. I mean, I'm just putting in numbers. Like I said, even
No,
for the
but there you already put in the non-relativistic potential, and from there you derive.
yeah,
But
so
but
even
one has
for
to be
even
careful. One has to be
yeah, I
careful.
agree. I agree.
Yeah,
Even for,
sure.
like I said, even for thermonium hybrid, you compute roughly 1 by R, which is of order MV. You do find it is greater than lambda QCD for the lowest thermonium hybrid, or it is roughly of order lambda QCD. You compute the kinetic energy. You solve the Schrodinger equation. We solve the Schrodinger equation. You compute the kinetic energy,
No,
which
no, but when you solve the Schrodinger equation, you're already assuming it is non-relativistic. So the values will come to be non-relativistic.
I mean,
But
like I
my
said,
question is whether you can use that. That is the whole point.
at some point like I said, at some point we have to start with something. So
Yeah,
the
but we
system,
know that it
we
doesn't work. The NRQCD is not a good formalism for charm. We know that from several different studies. So that's why I was asking you. Anyway, you
okay.
please continue.
Anyway,
Yeah.
anyway, like I told you, if I give you the sense of numbers, we verify the numbers, and I'm not saying we don't have to be careful for the charm case. We have to be careful, depends upon the observable. But for low-lying charm case, it does work. I mean, the numbers are satisfying the hierarchy that I mentioned.
Yeah, please. Yeah.
So the bound state dynamics is focused at the scale MV square. And the point is we are starting up with QCD, integrating out the mass of the heavy quark, which gives me the NRQCD. And then we integrate out all the higher energy scales, which include the lambda QCD, and end up with only the scale at MV square scale, which gives me the Born-Oppenheimer. So BOEFT only describes bound state dynamics at the scale MV square. There are a bunch of quantum numbers that I need to define in this Born-Oppenheimer EFT, because the point is once you have a heavy quark, heavy anti-quark, you have a preferred axis. So for finite separations of heavy quark, anti-quark, your spherical symmetry is broken down in the static limit. So spherical symmetry is broken down to the cylindrical symmetry. And instead of the angular momentum, the projection of angular momentum along the heavy quark, anti-quark axis is conserved. There is the CP is conserved, not individual C and P, but the product of parity and charge conjugation is conserved, and there is this reflection quantum number that is conserved. So as an example, I give you how to compute, like starting with some light quantum numbers, 0 plus plus or 0 plus minus, following this strategy, how to compute these Born-Oppenheimer quantum numbers. And again, in the R tending to zero limit, when you have the heavy quark anti-quark separation going to zero, the spherical symmetry is restored, and your system is described by your quantum numbers like KPC are good quantum numbers, and F stands here for the flavor of the isotopy. So the exotic hadrons that I want to address in my picture are all of these states, depending upon what the X is. It could be gluon, it could be two light quark pairs, it could be three light quark pairs. And the same thing can be done also in the sector with heavy quark, two heavy quarks and light quark. So here the color degrees of freedom has to be accordingly adjusted, like it's color triplet or sextet. In the heavy quark anti-quark sector, only the color octet is relevant for the exotic. The color singlets are going to give quarkonium plus pion or quarkonium plus proton. These states are not bound. We know from lattice QCD, a couple of lattice QCD calculations have shown that these states are not bound. And so color octet is what will be relevant for. In the literature, we call these states the light quark states basically. So X8 is referred to as adjoint hadrons. Just with gluon, it is dual glue lumps. With light quark pair, it is called adjoint mesons or adjoint baryons. And same is with triplet and sextet. So in principle, if I have all the lattice inputs that I need available, then I can use the lattice inputs to describe Born-Oppenheimer. But that's not true. I mean, there are lattice inputs not available. So let me start on the BOEFT Lagrangian. So in the individual Lagrangian, I have my Quirkonium Lagrangian, I have my hybrid Lagrangian, I have my tetraquark Lagrangian at lowest order. So for example, I have a Lagrangian that will describe my J psi. I will have my Lagrangian that will describe my lowest germanium hybrid or bottomonium hybrid. I will have my Lagrangian that will describe my lowest tetraquark. And then this is at the lowest order, but like the question came up, I mean, at some point of time, there are these excited charmonium states that will mix with hybrids or tetraquarks. And so the gap of order lambda QCD is no longer satisfied. And therefore, these mixing terms have to be added to describe into your system to properly describe the system. So the examples of the mixing are hybrid Quirkonium mixing, tetraquark hybrid mixing, tetraquark Quirkonium mixing. We will see an example of tetraquark Quirkonium mixing for the Chi-C 13872. Hybrid Quirkonium mixing is something that has to be studied as a future work, or tetraquark hybrid mixing is a part of the future study, basically. So on the left-hand side, I'm showing a plot of the potentials. So the lowest one is the Cornell potential. There are these states in these Cornell potential. The next ones are the hybrid potentials. There are states in the hybrid potentials. And as I said, J psi is not going to talk to hybrid because the gap is much, much larger than lambda QCD. But an excited Quirkonium will talk to hybrid, and that is what hybrid Quirkonium mixing will focus on.
How do you get this hybrid potentials?
You compute in the lattice. I mean, you have. If you give me some time, I'll touch upon it in the next few slides.
Okay.
I mean, this is,
yeah, sure. Yeah.
So so just before answering the potential, let me just show the Born-Oppenheimer EFT Lagrangian. There is nothing to be scared of here. Psi is the hadronic field, which is the Born-Oppenheimer, which is my hadron field here. It is the non-relativistic effective theory. So equations of motion will give me Schrodinger equation. Couple of things to focus on this Born-Oppenheimer EFT Lagrangian is that the kappa captures the light degrees of freedom. So we are summing over Quirkonium light state. We are summing over the light degrees of freedom in Quirkonium, in hybrids, in tetraquark, in pentaquark, and so on. These projection vectors are introduced because we want the correct BO quantum number. So these projection vectors are to cut these correct lambda sigma eta notations. And this potential here, V kappa lambda lambda prime, can be systematically expanded in order 1 by m series. So the first term is the static energy, and the next term are the spin-dependent potentials. You can go higher and higher order terms, but generally these two are the most dominant terms that would be relevant for describing spectrum or even the degree. The static energies, as I show in the previous slide here, a couple of static energies are degenerate at short distance. So some of the static energies with same light quark quantum numbers are degenerate in R tending to 0. So before answering your question on potential, let me just get to the Schrodinger equation, and immediately is the potential. So this is the radial Schrodinger equation that we get as an equation of motion from the Born-Oppenheimer EFT Lagrangian. There is this complicated angular part, which is first of all the angular term that is mixing several of the degenerate static energies corresponding to same quantum number, light quark quantum number. So these are coupling different static states. And the reason to understand this, why this happens, because my angular operator is spherically symmetric, whereas my static states have cylindrical symmetry. So this is why the mixing, the difference in symmetry is why is mixing happening. And there are these bunch of good quantum numbers that I define here. So just to inform you, I mean, one can use, so you can treat the heavy quark, anti-quark as a rigid rotator system, and you can derive these angular parts. So this was done in this long paper. I won't go into the detail. But the point is, you give me whatever exotic you want to describe, give the corresponding light quark state, the light degree, total light degree, light quantum number, and I can immediately give you what the Schrodinger equation is. So here is the Schrodinger equation, for example, hybrids or tetraquark, which have gluons or pair of light quarks. That means the light quantum numbers are integer. And these are the Schrodinger equation that comes out from the equation that I showed you. And these are the coupled Schrodinger equation, for example, in the case of doubly heavy baryons and pentaquark, which have fractional light quark quantum numbers. All of these Schrodinger equations, the main input that is needed are these E, K, eta. For example, maybe see, I can use the pointer, sorry, laser pointer. Yeah. The main quantity are the static energies that we don't know, and this is what I will touch upon next. One should note that the static energy does not include spin-dependent corrections. So these are for spin average spectrum for the time being. The spin-dependent corrections appear at order 1 over m, and therefore these will be either treated in perturbation theory or they will be included later in the study. But this is for the spectrum. This is for the spin average. Okay, coming back to your question, how do we compute the static energy? I will just roughly outline the procedure. So we start with the NRQCD Hamiltonian. The 0th order Hamiltonian is my static Hamiltonian, and then there are these 1 by m corrections, which include the spin. Here, psi is the 2-component polyspinor field. It's not the 4-component Dirac field, it's the 2-component polyspinor field that annihilates heavy quark. And chi is the 2-component polyspinor field that creates an antifermion. If you go into the static limit, which means throwing out these higher 1 over m toric sums, taking the heavy quark mass limit to infinity, the NRQCD Hamiltonian just reduces down to this H0, which is only containing the light quark and the gluons. And you can define a bunch of eigenstates theoretically. We do not obviously know what these eigenstates are, I mean, in the practical sense. For example, these n x1, x2 are encoding the pure gluonic content. These are the eigenstates of the NRQCD Hamiltonian. x1, x2 is denoting the position of the two heavy quarks, the static heavy quarks and antiquarks. And you can define normalization condition technically in the usual sense of quantum mechanics. So if I want to describe my exotic states, I can write exotic states as a superposition of all these static states, where for example, the n equals to 0 could correspond to a Quirkonium state, n equals to 1 could correspond to a hybrid state, n equals to 2 could correspond to could have better overlap, let's say, with the tetraquark states and so on. So this is like the spectral decomposition that I'm performing. And the vacuum expectation value of this Sk time order vacuum expectation value is proportional to this exponential of this energy. I mean, the En0 are the static eigenenergies of the anarchist static Hamiltonian, and eventually in the large time limit, the static energy will be just given by this correlator. So I will touch upon the correlator. What is the expression of the correlator that we use, for example? So just give me a second. So this is just the definition that we use, for example, in the quantum mechanical side and Heisenberg picture to describe what is the expression of the static energy in terms of the states, for example, the exotic state that we want to describe. There are a couple of things that I want. The two-point correlator here is a function of several is a overlap on or is a linear superposition of several n values. Obviously, we want the lowest one, so we have to choose our exotic state operators in such a way that it has better overlap. Let's say on the hybrid, then n will be some specific number, or it has better overlap on Quirkonium, then n will be some specific number. And this is what is basically required. So we need to choose our operators very carefully to get these static energies. So now the question is, what is this state xk is? What is this operator that we choose? So in NRQCD, I can define and gauge invariant operator for the exotic hadron. So here is my operator that has heavy quark. These Wilson lines are added just for the gauge for the gauge invariance, basically. So this is the spatial Wilson lines, and this is the part in my blue color is the light degree of freedom, which is containing all the information about either the light quarks or gluon into the system. So I have my heavy quark at position R half. I have my heavy anti-quark at position minus R half, let's say. So the separation between the heavy quark is R. The relative separation is R. I introduce my light quark business, and the states are basically The states that I showed you are basically created by these creation operators or the operators that are the NRQCD operators that I'm showing, and this 2-point correlation function eventually reduces down to a Wilson loop. So this is the Wilson loop that one get in the case of the quarkonium. In the case of exotic, this is the Wilson loop where you need to insert the light quark into your system. Here I insert my light quark at position 0, which is in between a heavy quark and heavy anti-quark. You are free to insert anywhere you want. The only point is that everything has to be gauge invariant, so you need to choose, accordingly. So you mean if you insert at different positions in R, you may need to add several combinations to get the gauge invariance out of the thing. So this is how the static energy reduces down to. It is basically the computation of Wilson loop either on the lattice. Specifically on the lattice that has to be computed. Perturbatively, we obviously can compute the Wilson loop. The point is, if you do the computation of the perturbative computation of the Wilson loop, you get only the Coulomb part. You do not get, for example, in the case of quarkonium, you will never get the confinement part. So
Abhishek, so when you mention you're inserting the light quarks,
yeah.
So what specifically do in your formalism?
So for example, here is the expressions of the light quark that I introduced. So for simplest case, in the case of quarkonium, which is given by 0 plus plus, a scalar representation for the light degrees of freedom, the operator that I insert is just 1, nothing else. So it is not, it's just the identity. Now, if I want to describe, for example, let's say the lowest one, which is the pseudo vector here, the last row of my table here, which is 1 plus minus. The quantum number is corresponding to inserting a magnetic field. So I insert a magnetic field operator, or in the Wilson line, in the lattice case, okay, I am using the operator B field, but on the lattice, okay, they use some. I'm not a lattice expert, but they, there's a specific way to represent B field using gauge links. So they use these gauge links to represent.
Yeah, this is Clover improve. You can
Clover
put in links, or you can do Clover improvement. That is fine. But then you are taking that. They correspond to the same quantum numbers as these states. So B is pseudo vector, so you're putting that.
Yeah. But you are free to see. You are free to choose anything you want. The point is on the eventually what we want to get is the quantum number. The quantum number is important. So 1 plus minus, the simplest quantum number I can write is the magnetic field. But there are other operators that I can obviously introduce, which will give me the quantum number 1 plus 1. For example.
But I'm just trying to understand, why do you say it is having the same effect as inserting the light quarks? Because light quarks also have a dynamical part.
So this is for the hybrid I was telling. This is now the light quark part. I'm coming back to it. So
Okay.
this is the
glue. The glues.
So the part that I was describing is pure gluonic theory. This is just describing the hybrid.
In the gluonic theory, how do you, in what gauge are you doing these things, calculations?
This is Wilson loop is gauge invariant.
That is fine. When you put in the magnetic field, then you are putting in this is not a gauge invariant object.
So, this whole operator, the O kappa lambda is gauge invariant, including the magnetic field. So this whole thing is gauge invariant. This we prove. Then you can obviously work in Coulomb gauge or whatever, this axial gauge, whatever gauge you want to choose. But this as just individually, magnetic field is not gauge invariant, but obviously this O kappa lambda is gauge invariant.
Is O or the whole correlator is gauge invariant?
The left hand side. The whole correlator is the correlator transforms.
The correlator is when you take the correlation function, then it is always gauge invariant.
That is what I'm saying. The operator as such transforms in a specific way, and then when you take the correlation, it is gauge invariant. This is the Wilson loop is gauge invariant. That's what my point is.
The operator is not gauge invariant, is it?
It has a specific way of transforming in like you can. It is not. As such, it is not gauge invariant. It's gauge covariant. I should mention that it's gauge covariant. So it has a specific way of transforming under gauge transformations.
But when you said, this operator creates this physical state.
No, the
Physical
operator.
state has to be, should not know anything about, what is inside, whether it's gluon or quark, because these are all color
I mean,
degrees of freedom, no? But you
yeah,
said,
yeah,
O acting on a vacuum
yes.
creates your some whatever exotic state.
I mean, it's not.
Physical state,
It is.
and
It
it
is.
should not know anything about, what gauge you choose to compute that, right? In
So
principle,
I do not.
state.
I do. Yeah. I mean, I'm not. Yeah. I mean, O acting on vacuum creates something that is
That's
something like an exotic. Yeah. Something mimicking the exotic state. Um.
mimicking
I
means
mean,
what actually? You have to create a state, no? If you are calculating some overlap between
yeah.
two,
I mean, so we
you are
create.
dealing
So
only with some states which are actually hadronic in nature.
yes.
You create it using some operators acting on vacuum. Both
Yes.
are actually, in my opinion, no physics in it, but
Yes.
the combination is what it gives you physics.
Yes.
Individual components may have no meaning
No.
to
No. No. No.
specific observable effects.
No.
Yeah. So if why you said correlator is gauge invariant, even the O acting on vacuum also should be.
I
Maybe
mean,
I'm missing something. Maybe you can explain.
what I basically mean is eventually like on the, for example, let me just explain in the terms of the Wilson loop here. So on the left hand side, we have a source for creating a heavy quark anti-quark pair. So at minus t half, we have a heavy quark anti-quark pair source. At plus t half, we have a sink for heavy quark anti-quark pair. The Wilson loop is basically evolving from minus t to plus t. This whole Wilson loop is gauge invariant.
I see. Okay.
So that is what I want to emphasize. I mean, this is the point that the Wilson loop is gauge invariant. It's the same thing happening in the case of exotics. You create a heavy quark, anti-quark source with a light degrees of freedom at minus t half. You also do the same thing at plus t half. You do the time evolution. The Wilson loop that you eventually get is gauge invariant. This is what my idea is basically.
Sorry to interrupt. So when you said about these exotic parts on the right hand side, when you create this heavy quark anti-quark pair together with the light degrees of freedom, the question is, shouldn't the left hand side of the right hand side diagram itself be gauge invariant, because that's actually a hadron, which is a color singlet object, right?
I think it is gauge invariant. I mean I
I
have to
believe
go
it is
back and
gauge
check.
invariant. It is
Yeah,
probably, yeah, it is gauge
I mean
invariant.
it
O
is
is
gauge
also
invariant. I mean I will have to check. I mean, I'm pretty much sure what we are doing is a gauge invariant. There is no specific gauge involved. I will have to just right now. I mean,
But
I'll have
this,
to walk down and see.
sorry,
But
this operator that you had written down on the top of the page,
O should be gauge
OK
invariant.
it should
lambda,
be
is it a
technically.
gauge invariant object or non-gauge invariant?
I think it has to be gauge invariant because, like Padmanath mentioned, it has a color singlet state.
That's a reason actually, but I'm saying by constriction,
Yeah,
as chi and psi, they have a specific gauge transformation property.
yeah. But then,
Phi is also as something, P as something. I don't know all these, symbols.
So
But,
for example, chi and psi are the non-relativistic field. They transform under like psi transforms as u psi, chi dagger will transform as chi dagger u dagger. The Wilson line transforms as a d mu operator, so it has u phi, u dagger, and the H transforms in analogous way. So eventually you will find that it is gauge invariant. I mean,
by construction, O is gauge invariant.
yeah,
The
by
vacuum is also
construction it is, I
gauge
think,
invariant.
gauge invariant. Yeah, I mean, I
Vacuum is
just have,
gauge invariant. So the action of O on vacuum is also gauge invariant. Is that
yeah,
how
that
I
is what.
understand actually? Yeah.
So
Okay.
you work out the gauge transformations of psi, chi, and the phi is the Wilson loop. You will find, I think, it is the gauge invariant operator.
So this phi is introduced to make this entire
If you remove phi, if you remove phi, then it is not gauge invariant. The phi is introduced to make it gauge invariant. The Wilson loop, the Wilson lines are introduced to make
yeah,
it gauge
that
invariant.
is probably I would understand, that way. Yeah, okay, then it's fine. You
And
said
then
actually you can compute, not using lattice. How do you compute this without using lattice actually? Because
we
this
do not compute. No, so like I said, for example, in the case of Querconium, you can compute. You can compute the Wilson loop for Querconium perturbatively at orders in alpha s. You will get the Coulomb part, but you will never get the confinement part out. The lattice is the only reason why we get why we see the confinement added to the Cornell potential, or why we see the confinement in the case of Querconium. So perturbatively so eventually these Wilson loop is a closed path of some exponential of gauge field. You expand the exponential at each order in alpha s, the strong coupling constant. What you will get are the Coulomb potentials order by order, higher orders in alpha s, but you'll never get the confinement part out at fixed order in perturbation theory.
That means you can't compute. No? That's the statement. That
I
means you
mean,
can't compute.
You can't you can compute the perturbative part, but you cannot compute the confinement part. That is what more accurately I want to put.
Okay.
So in the case of Perconium tetraquark, these are the operators that I write down. I mean, just to show you what are the operators that we write. And in the pentaquark case, this is a more horrible operator because the 3 light quarks have to be satisfy Pauli exclusion principle and all these criteria. So all these things have to be satisfied. So just complicates things. Anyway, in the QFT perspective, so I show you the perspective from little bit on the spectral function of the matching side. In the QFT perspective, what we do is we write down the 2-point Green's function in NRQCD. I won't go into the detail because this involves a lot of technical things. And on the Born-Oppenheimer EFT, I write down the 2-point Green's function in Bow EFT. So I write down, for example, psi dagger. In the NRQCD side, I write this O dagger operator, and I match these 2-point Green's function. For doing short distance expansion, we use multipole expansion. I'll explain what I mean by multipole expansion in just the next slide. And the matching will basically give me the connection between the static energies and the Born-Oppenheimer potential. So this is the perspective from the QFT matching calculation. So I just show you briefly what we do in the QFT side. So we have, so for example, take the exotic states in the color octet, for example. I write this operator O kappa lambda on the NRQCD side. Maybe just do the expansion here. Yeah, I write the operator on the NRQCD side. I do the multipole expansion, which is expanding in terms of color octet, heavy quark, anti-quark pair, and this light quark pair field, which is either gluon or light quark. And then on the other side, we match onto Born-Oppenheimer EFT. So this multipole expansion is only short distance expansion because at short distance, we know that the potential is given by some Coulombic potential given by the corresponding to the color degree of freedom. So the short distance expansion is just to get to that part. In case of Perconium, this heavy quark anti-quark pair are in color singlet. So you have at short distance a singlet of field, and eventually you match onto, for example, a Born-Oppenheimer field on the right-hand side. So this is the matching that you do, and you compute this 2-point correlation function now.
Sorry, can you explain this multipole expansion a bit more? What you're doing?
Yeah, exactly. Can I explain in respect to this, basically?
Yeah, sure.
So the multipole expansion is using the fact that so I want to eventually get to the static energy. The static energy is a function of separation R. It contains the information basically where the heavy quark anti-quark pair are at short distance where the separation is 0. It also contains the information where the heavy quark anti-quark are far apart. So the multipole expansion is just getting to the short range behavior. So it's an expansion at each order in R. So for example, the static energies will be at order R square or order R is to 4 or order R is to 6. So what happens is your heavy, so again in the context of Perconium, you have a heavy quark anti-quark pair, and in short distance you find that they are in color singlet. So you have the heavy quark anti-quark in color singlet configuration. When your heavy quark anti-quark are far separated, there is a flux tube between it. You cannot explicitly define that the flux tube is containing a specific color. It contains every possible color it wants, but only at short distance limit, the color is specifically defined. Again, in the case of exotics, I have my heavy quark, anti-quark, and light degree of freedom. I have my heavy quark, anti-quark at short distance in color octet. So this is in the R tending to 0 limit. And again, when I have the separation far apart, there is all sorts of QCD dynamics going on that that we cannot describe, and that this is where lattice basically helps us. So when we do the multipole expansion, what we find, for example, in the case of Perconium, a 4/3 alpha S by R, the singlet potential, plus higher order in R square expansions. In the case of exotics, what you find is an octet potential because I have the octet degree of freedom, plus a mass corresponding to the light quark pair or a gluon plus order R square terms. So the order R square is coming from a singlet getting polarized to, for example, octet, and octet is getting back polarized to singlet. So we are inserting like a dipole term into our theory in the multipole expansion in a way. And in the same thing will happen in the doubly heavy quark system where your color degrees of freedom are triplet or sextet. And this lambda HK is defined by this 2-point correlator involving only the light quark fields where this phi AB is my temporal Wilson
Abhishek,
line.
sorry, I just wanted to know, you said the short distance R tends to 0. With
Yeah.
respect to what? If we are doing a expansion and say,
So the R is only defined between the heavy quark anti-quark pair. So the R is the separation between the heavy quark and anti-quark. So the R
that's fine.
Yeah.
My question is that when you are doing an order by order expansion, if it has some certain units and etc., you are usually comparing it against certain other length scale or something like that. In this case, what is the length scale you are
So for
referring
example,
to?
the length scale, the exotic. So for the length scale, for example, associated with thanks for this question actually. So the length scale associated with the light degrees of freedom is 1 by lambda q.
Okay.
So I'm describing short distance, but when I mean short distance, I'm going in limit where R is much less than lambda q, 1 by lambda QCD.
Okay. Much less than 1 by lambda cube.
Lambda QCD.
Lambda QCD. Okay. Lambda QCD. Okay, I understand.
Yeah, lambda QCD. So lambda QCD is the scale. Lambda QCD is the scale of the light degree of freedom.
Yeah.
When I mean short distance, I mean I am taking my heavy quark anti-quark to 0, which means my R is much less than 1 inverse of lambda QCD scale.
Okay.
When I'm saying long distance, then I'm basically saying R is of order lambda QCD inverse or much greater than lambda QCD.
Okay, and you are keeping it up to the quadratic term in 1 by lambda QCD, right?
Yeah. Eventually, I mean, I'm just showing the short distance. Eventually, for the calculation purpose of the spectrum, we fit to the lattice data, which eventually covers all the parts out. So I just want to give you the idea that why in short distance we get this singlet octet or degree of freedom. You cannot define a singlet octet in a flux tube. I mean, the flux tube will contain all possible configurations of color.
Okay.
Yeah,
okay.
I have one question. You have put in a box at the top right corner.
Yeah.
Various types of potential terms actually.
Yeah, I mean, basically defining the perturbative potentials.
What is the basis for all this?
What do you mean?
It looks like some exact result actually is alpha S by 3R.
I mean, this is based on the color. The factor, the alpha S by R is okay. For example, in the QED we have alpha S by R. Then these pre-factors like 4/3 or 1/6 or 2/3, they are coming from the color degrees of freedom. Okay. In the singlet, for the singlet we have this 4/3. For octet we have 1/6. For triplet, color triplet we have minus 2/3 or 2/3, and one for the sextet it is 1/3. So it's just color contractions. You take some trace of color matrices, and these are the color degrees of freedom.
But these are exact results, or
these are exact results. I mean, these are exact results. This is the singlet.
They don't get corrections from
I mean, the alpha, the alpha. Obviously, they will get corrections. You can go. The alpha S here is.
So it's a leading order potential.
It's a leading order. Yeah, it's a leading order, but you can include higher and higher order corrections in alpha S.
It's not exact result. That's my question.
Okay, I mean, if you just take minus 4/3 alpha S by R, then it's the leading order exact result. Then you can include alpha S square corrections, alpha S cube corrections, depending upon what you want.
For this approximation, this is sufficient.
Yeah, this is sufficient. I mean, this is, so there's a question, somebody raised the hand. So
this was me.
Oh, okay, I'm sorry. Okay.
Abhishek, so what is the value of lambda QCD are you taking here?
I mean, lambda QCD for us is the hadronic scale. So it comes from something like proton mass is the order, or rho meson mass. So 700 MeV to 1 JeV. But
then 1 by 700 is almost like 1/5 Fermi or something. Or 1 JeV. Yeah.
I mean the short distance, like I said, so when we take the potential into our spectrum calculation, the short distance expansion is only valid for around 0.1 Fermi. And then everything is long distance. I mean, just give me a few minutes. I'll go to the application of X, and then you will see the long distance potential and short distance potential both coming into picture. Okay, this is the last theory part before going into the application. So this is studying the semi-inclusive decays, where we study the exotics going into zirconium plus Y. My Y is any light hadron, and we can do this calculation in perturbation theory, again using multiple expansion in some ways, where we specifically have these color degrees of freedom, octet, singlet, octet transitions. This is because the large energy gap between the hybrid and the quarkonium. So my quarkonium is a low-lying quarkonium state. So for example, J psi or maximum is psi 2s or 1p quarkonium state. Because in those cases, the energy gap is of order 1 GeV. You can perform a matching calculations between this something called as the P in RQCD, potential and normal QCD, which is the multiple expansion here, and Born-Oppenheimer EFT, where you compute this one loop diagram in this multiple expansion using multiple expansion P in RQCD method, and you match onto this imaginary term. You cut it, and the cutting will introduce an imaginary term in the hybrid in the exotic potential. And you use the optical theorem to relate the decay rate. So just a disclaimer to be put out here is that the fact that this method is not useful for example, if you want to compute exotic states decaying to threshold pairs, because the energy gap is not results. If we follow this, we get the results for the semi-inclusive decays. This involves the either spin conserving decays or spin flipping. When I meant by spin conserving is the heavy quark pair spin is conserved in both the in the initial state and the final state. So, and the spin flipping basically means the heavy quark spin is flipped because of the S dot B term. So one is introducing an electric dipole, another is introducing a magnetic dipole in a simple way. And because we are only computing the decays to quarkonium, we are getting the lowest bound on the total width. So it is not the complete inclusive rate, but it's setting the lower bound on how much the width could be. Okay, so now I'm showing the application of the X to X and TCC. Maybe just let me show the X and I'll skip the TCC part. So in the case of tetraquark, the static energies, this is the new prediction from the Born-Oppenheimer EFT. The point is, in the case of tetraquark, what we find is that we have a 4-quark system where if I take my heavy quark antiquark to be far apart, I will have 2 color singlet states, which is corresponding to meson pairs. So I have 4-quark system that breaks down to D or D bar meson, or a B and B bar meson as R tends to infinity. I have 2 color singlet hadrons going on. And what you find interestingly is that when you write the Born-Oppenheimer quantum numbers for the system at finite R and the Born-Oppenheimer quantum number for the meson pair. So I'm showing the example of the Born-Oppenheimer quantum numbers for D and D bar meson, D bar threshold here. They are the same and they are the same on both sides. So meson and anti-meson have same BO quantum numbers as of the adjoint meson at short distance. If I introduce quarkonium and tetraquark, what we see from the lattice is that, for example, I have 2 quarkonium states. If I keep on pulling, the string will eventually break and generate the meson pairs. And the impact of generating these meson pairs is you get these avoided crossing curves at some finite values of R. This value of R is about 1.22 Fermi. This is a large distance effect because 1 by lambda QCD, as somebody pointed out, is of order like 0.2 or 0.3 Fermi around. So this is a large distance effect that comes into picture into your static potential. And the way one can explain this avoided crossing effect is because the Born-Oppenheimer quantum number for the meson pair and the quarkonium is the same. It is this sigma G plus that is introducing, that is basically having the avoided crossing.
Sorry, just to ask you, so for the light hadrons, the average radius is around 1 Fermi for proton and pions and all. They're roughly the same. And that corresponds to lambda QCD as we define, which is around 200 MeV or 300 MeV of that ballpark. Now here, when you mention the string breaking happening, that radius 1.22 Fermi, whatever, that is the typical size of a light hadron of the order of that. So wouldn't the lambda QC be defined in terms of that scale? Because that's how we
I mean, if you take, and the proton mass is the lambda. I mean, you can take lambda QCD. I mean, the lambda QCD scale depends upon the hadronization. Yes, the rho boson mass is not something.
Not
Is
the
not.
mass. Why should we consider the mass for the lambda QCD scale?
I mean,
I would.
The proton is not perturbative. Yes, the proton is 1 GeV. We do not consider proton to be a perturbative.
No, but that is not the point. The point is the radius beyond which your string breaking happens, which is around 1 Fermi. That is corresponding to the confinement scale, which is inverse of lambda QCD, right?
Yeah, for example, yeah, I mean, 1 Fermi is already a very large distance effect. For example, psi 2s. You can take that the lambda QCD scale is the scale where your linear part the linear part of the potential gets important. And for psi 2s,
that is of the order of 1 Fermi around.
No,
or of the order of that.
Less. Yeah, I mean, it's around point. I mean, for example, psi 2s has a radius of about 0.5 Fermi. It is already important for psi 2s to account for the string, to account for this linear part of the potential. So, I mean, the lambda QCD scale, as I mentioned, is roughly, I'm taking the hadronization scale. It could be the pion mass, it could be the proton mass, and proton is also
Sorry, it cannot be related to the pion mass. It's related to the inverse of the pion radius, not the mass, I think.
When pion mass is roughly 150 MeV, I'm talking about the order of magnitude here. So,
but not the proton. If you consider proton mass, that is 1 GeV. So, and the radius of proton is not about 1 GeV inverse, which is like 1/5 Fermi.
Yeah, I mean, the radius is always an order of magnitude. The order of magnitude can be a factor of 2, can be a factor of 3. I mean, like I mentioned, for psi 2s, whose radius is roughly around 0.5 Fermi, already the linear part of the potential is important. So only for like J psi and psi 2s, J psi and upsilon 1s, for example, you can use only the perturbative potential, the 4/3 alpha S by R.
So when you tell linear part is important, this linear part is of the string breaking part or the
the string breaking. I mean
the Lucia term.
I mean the linear part in the Cornell potential, for example. The string breaking is a effect that is arising because
that I understand, but that scale is fixed. This potential is fixed for any quark anti-quark pair, heavy. Yeah.
The potential is fixed for any quark anti-quark pair. Like I said, if you take upsilon 1s, you can describe the upsilon 1s by ignoring the sigma r part in the Cornell potential and just using the minus 4/3 alpha S by R. All perfectly fine. You can even do it same for J psi. For psi 2s or even for 1p, you already see that the confinement part of the Cornell potential already starts to get important. So it's not true that, okay, I mean, that lambda QCD is of order only 200 MeV we will take, and so we can describe using lambda QCD as 200 MeV. I mean,
no, but the potential is fixed. It depends on how large is the radius of this bound states. So that will feel which part of the potential is important, right?
Exactly.
Yeah.
So I mean, depending, I mean, as I said, I mean,
it's not that the potential is different for J psi. It only depends on the size of those objects.
Yeah, I mean, it only depends on these energy levels, as I'm showing here. For example, in the Corkonian state, it only depends upon the energy levels. So energy levels and the size of this bound state object in those energy levels. So,
yeah.
Sorry, it was far off. Yeah, so 1.22 Fermi for us is already a large distance limit for us. I mean, this is where already you see the meson pair starts to enter into your picture. And that is where just after 1.22 Fermi, the energy is just given by twice the meson system. So this is the bending that one sees into the calculation. So 1.22 Fermi is roughly like R tending to infinity for us in our case. I mean, just to compare, I mean, do not compare it in the absolute sense, but if you take this figure, I mean, you see the Quirkonian potential is bending, and the bending is around twice the meson pair mass. So this is the prediction that we make in the Born-Oppenheimer EFT based on the symmetry. So you have something at short distance, a Born-Oppenheimer quantum number at short distance. You write the corresponding Born-Oppenheimer number at long distance, And the Born-Oppenheimer quantum number has to be conserved. This is the pattern that we see in all the lattice calculation in all the molecular systems. We do not understand why at present, but this is the pattern that we see in the case of, for example, atomic system in the lattice QCD calculations of hybrid potentials, or the example of this string breaking that I mentioned. And because the Born-Oppenheimer quantum number has to be same, you match onto the short distance. You have a short distance constraint, you have a long distance constraint, and then in between you can draw your behavior as you want. So this is the diagrammatic pictorial representation of the potential I am showing. The key takeaways that one should take away is that, for example, this holds for pentaquark potential also. This holds for doubly heavy baryon also. This holds for any state that you want. So, for example, with respect to tetraquark, the key takeaway is that the static energy behavior is repulsive at short distance. It matches onto heavy meson or baryon pair threshold at large R. So baryon will enter when I take pentaquark states, and avoided crossing with quarkonium with the same Born-Oppenheimer quantum number. The point is BO quantum number and the tetraquark quantum numbers are the same, and therefore there is avoided crossing. If the quantum numbers are different, there would be no avoided crossing. They can cross each other. So this is the no avoided crossing theorem in like molecular systems. So this is the new prediction based on the theory. The lattice has not confirmed it. We know that these results hold in certain limit. There are preliminary calculations that indicate that this result is true, but nobody has seen this short distance behavior. So, for example, as you see, the short distance behavior of the tetraquark is noisy because of the ground state plus pion configuration, and so they don't go beyond certain values. So we actually predict the short distance behavior based on the theory constraints. So X3872 is the first exotic state, as I mentioned. It has quantum number 1++, and the quantum number indicates that the heavy quark pair orbital angular momentum is 0. The state is extremely close to the threshold, just about 100 keV below the threshold. And in our Born-Oppenheimer EFT, when you write the quantum number of the multiplets that we get for tetraquark, we get this lowest multiplet in the tetraquark, which has this 1++ quantum number corresponding to X. From the lattice, I do not know my 1 adjoint meson mass. I take it as a free parameter. I have to choose it as a free parameter, and I fix on X3872 to give a prediction on the adjoint meson that can be confirmed by lattice at some later point of time. So this is the coupled channel Schrodinger equation. The Schrodinger equation accounts for the quarkonium potential because, as I mentioned, at some distance, the tetraquark is going to mix with quarkonium. This is the about 1.2 Fermi. So this is the tetraquark quarkonium mixing accounted into picture in the Schrodinger equation. And then there are these two potentials that I have corresponding to the tetraquark, corresponding to this 1 adjoint meson. So these are the two static potentials that are entering into picture. So you solve the Schrodinger equation. Okay, we have a way to parameterize this mixing between the tetraquark and quarkonium using EFT arguments. We try different behavior of the mixing. The result does not change. The result is absolutely stable against any behavior of the mixing potential that you want. And here, the short distance part, I mean, the specific expressions, if you want, it's in the backup slide, but the short distance is the short distance is only until 0.1 Fermi, and the long distance is given by 1 pion exchange between the DD mesons for the tetraquark. So you solve this coupled channel Schrodinger equation, though there are technical challenges in solving multiple in the case of X because the state is extremely close to threshold. So I developed the code to solve for the bound state situations for states which are extremely close to threshold. You solve this, you get a 2p quarkonium percentage in X, which is about 10%, and tetraquark percentage to be 90. You get a radius of extremely large radius for this state because the binding energy is 100 keV, because that is what we fix upon to predict the adjoint meson mass, which is minus 228 MeV. Note that the negative value is corresponding to the fact that I have my threshold shifted from some value to 0. So the negative is because my threshold is now at 0. If I move my threshold to the corresponding value in PDG, then I'll get some positive number about 930 MeV or 920 MeV. We also study the spin splittings because all the four states obviously cannot be X. The X is the only state that exists close to the threshold. Other states are far away. So for the first purpose calculation, we account for the spin splitting in meson pair. So meson pair, note that the meson pair is only at large distance. So we account for the spin splitting in meson pair. This is an approximation that I'm doing. I mean, because we do not have spin dependent potential from anywhere. So this is a first order approximation. I'll come back to the spin dependent part later. If you do the first order perturbation theory in BSS, this is how the spin splitting effects looks like, where your X is immediately just below the DD star threshold. I mean, we show here a little bit of gap just to show the distinctness of X compared to the DD star, but the state is about 100 keV below the threshold that we find, and the distribution of other states after including first order perturbation. So we predict 4 states. If you do the same thing, so only X has been seen. All these 3 states have not been seen till now. And because we fix our adjoint meson mass on the lowest multiplet, which is including X, all other higher multiplets here will be unstable. They can either be resonance, they can either be states with very large width. We do not know, we have not explored, but this is something to be explored in the future work because there are some states in the multiplet that will correspond to the experimental states. For the time being, I will skip TCC because I think there's a time constraint. So the TCC is another state that was recently seen. We again do the same thing as the X case. The important point to note is that the TCC falls in the multiplet of good diquark that is defined in the lattice literature, and the bad diquark state will again be some resonance state or a state which is unstable. Again, when you solve it, you get a state which is about 8 Fermi. We do not know the good diquark energy from anywhere. I mean, so we again take it as a free parameter and fix upon the experimental result. So this is the prediction for the good diquark energy considering the DD threshold. Okay. And there are other bottom states that we predict that I'll not go into, but I want to delve into right into pentaquark state. So pentaquark states, there are 4 pentaquark states that has been observed. These states only involve up or down quark. They don't involve charm quark. They don't involve, strange quark. So the JP quantum numbers have not been established. All these pentaquark states have been seen as a narrow structure by the LHCb experiment. I mean, with more than 7 sigma confirmation. I mean, for some of these states. In the Born-Oppenheimer theory, you write the pentaquark multiplets. This is the recent paper that came in August. You write the pentaquark multiplet I have 3 light quarks here. The sum of 3 light quarks can be spin 1/2 or spin 3/2. So these are the 2 spin states of the 3 light quarks. And corresponding multiplet is written here, the corresponding quantum numbers, the final quantum numbers, JP of the pentaquark states. And because there are 2 light quark quantum numbers, you have two different Schrodinger equations into your picture. Again, you do the similar thing. You take this, we model our pentaquark potentials by short distance constraint, by long distance constraint, given the fact that all these pentaquark states have been seen near sigma CD threshold. So we model our potentials based on this large and short distance constraint. Again, the short distance is only up till 0.1 or 0.2 Fermi max, if I remember, and then the long distance is parameterized by 1 pion exchange potential between the sigma C and D bar. You can do the same calculation. Just let me say, you can do the calculation with 2 pion exchange. The results don't change at all. I mean, within 40 MeV adjustment, the results are stable. Yeah.
Why do you extend your calculation to so large distances like 2.5 Fermi and all?
I mean, I have a potential. Yes, I have the potential now. And I'm just drawing it for the picture. This is just the.
And how do you constrain this long distance part of the potential?
The long distance part of the potential is constrained by the fact that if you write the Born-Oppenheimer quantum number, so again, coming back to here, I'm again explaining in the context of tetraquark, the same thing happens in the case of pentaquark. So if you write the Born-Oppenheimer quantum number, for example, the DD bar threshold, it is the same quantum number that is appearing up as compared to the adjoint meson. So they have the same BO quantum number. So your potential has to smoothly transition from short distance to long distance. There cannot be any weird behavior happening because at short distance, let's say at finite R values, I have my 4-quark state. At infinity, I have my 2 singlet hadron states. So these two interpolate with each other smoothly. It's something like string breaking. Something like string breaking cannot happen. String breaking cannot
when you
happen.
have this two-level mixing and all, then in these kind of systems, when you have state crossing, how can you define the potential so well? I mean,
no,
always whenever there is this.
There is no mixing happening. What I'm saying is I'm writing the quantum numbers of my system at finite values of R, let's say at small r values. I end up getting these Born-Oppenheimer quantum numbers. The same 4-quark system, as my R tends to infinity, there are 2 color singlet states. I have a D and D mesons. I write the same quantum number for the DD bar mesons or BB bar meson, for example. I get the same BO quantum numbers. Now, for all values of R, the BO quantum number has to be conserved. This is the conservation is what we see in the case of hybrid potentials, what we see from molecular physics also. We do not have a deeper understanding at present why this conservation holds in QCD. This is something that has to be understood, but this conservation it happens as an example, like I told you, in the hybrid case, this conservation happens. In the molecular case, this conservation happens. So once the conservation happens, you just write, you just you extrapolate from the short distance, you extrapolate from the large distance, and you have an intermediate behavior. Intermediate behavior we cannot.
And when you mentioned that there is this conservation of these quantum numbers, is it an experimental fact or what?
There is no experimental fact. There's a lattice fact for the hybrid. So maybe let me just go to the hybrid case and show you. Okay, just give me a minute. I have to go back to my backup slides maybe. Yeah. So for example, this is the hybrid calculation of hybrid static calculations. These n values are string excitations because your heavy quark antiquark are far apart. So you model the flux tube as some string as a string excitation. You write the Born-Oppenheimer quantum number at short distance, which are corresponding to gluon quantum numbers. You find some lambda sigma eta notation. You write the corresponding Born-Oppenheimer quantum numbers at long distance, corresponding to these string excitations. There are articles on how one can get this. You find that it is conserved at all values of R. A pi u, for example, the red line here, the pi u at short distance goes to pi u at long distance. A sigma g plus, which is quarkonium at short distance, goes to sigma g plus at long distance. We see the same pattern, for example, in the case of tetraquark. These are preliminary results. For example, in the case of doubly heavy tetraquark, the sigma g plus potential of the tetraquark at short distance matches onto the sigma g plus of the DD bar meson. This conservation happens. I mean, this is a smooth transition that is happening just because I can create my 2 color singlet hadrons at infinity. I cannot do it for quarkonium. I cannot do it for hybrid. In the case of quarkonium, when I try to create that, I need to do this string breaking. I need to do something analogous of that to generate light quark pairs. But here, because my light quark pairs are into the system, I can smoothly generate my meson pair systems out. This is the calculation by Prelovshek in 2020. They could not go to short distance, but this is indeed, they say, this sigma u minus potential that matches onto the BB bar threshold here. So this is what we see in the lattice. This is what we see in the molecular systems in the atomic physics. There is no experimental fact. I mean, okay, so yeah, so we do the same thing for the pentaquark. We get the result for the pentaquark states. Again, we do first order perturbation theory in the spin splitting. Just to highlight what is the difference between model, the compact pentaquark model predicts 10 states. Some have positive parity. They construct some diquark, single quark system or a diquark, triquark system. And molecular model predicts 7 states, which agrees with Born-Oppenheimer EFT. You will see one beautiful example where the Born-Oppenheimer EFT actually differentiates the model. So using the semi-inclusive method, I compute the decay rates. On the left-hand side, I show the total width. whereas our total semi-inclusive decays just to J psi have been calculated. The pentaquark 5-half cannot decay to J psi, it will decay to eta C. We also get the results for the decays to lambda C d bar. The ratio here, we do not get the absolute number, but we get the ratio because there is a parameter that we do not know how to fix. So eventually in the ratio that parameter cancels. And similarly, we have results on the bottom pentaquark spectrum, semi-inclusive decays and ratios of decays. These all can be found in this paper. I will not go into the detail, but just to show you the results.
Abhishek?
Yeah.
It's already 1 hour, 15 minutes.
Yeah, so I'm just ending. I'll just end. So
okay, sure. Thanks.
Just give me 5 more minutes. Sorry.
Okay.
So this is the isospin 3-half pentaquark state that was indicated by LSCB. It has not been confirmed, not yet confirmed. This is isospin 3-half. They see a peak, they need to study it. In the isospin 3-half sector, Born-Oppenheimer EFT predicts only 3 states, whereas model will predict whether I think molecular model will predict 7 states. The 3 is only coming into picture because this 3-half is not allowed by Pauli exclusion principle when you take isospin 3-half. So you work out when you work out the details of the Pauli exclusion principle, this 3-half will not be allowed. That rules out these 4 states, and only the 3 states in 1/2 plus is allowed. So this is where the difference arises. Again, we do the same thing for the hybrids. We computed the spectrum, thermonium hybrid, bottomonium hybrid. We computed the semi-inclusive decays to quarkonium, compared with the PDG, made some interesting comments about which candidate could be the hybrid candidate. For example, this Psi 4230 on the left-hand side, the most left-hand side, was a prominent hybrid candidate for a long time, but our calculations indicate that it is not a hybrid candidate based on the calculation. And indeed, there are now studies planned to study it as a mixture of hybrid tetraquark quarkonium mixing. An interesting aspect, again, where Born-Oppenheimer EFT that we predict differs from any other calculations, quark model or anything. For a long time, hybrid decays to pair of heavy light mesons like DD bar mesons were not allowed. They were forbidden, but actually, again, just based on the Born-Oppenheimer quantum number, if you see, they would be allowed. So I write down which hybrid states. These are the hybrid multiplets which will be allowed or which will be forbidden. Only the states which have sigma u minus will be allowed to decay because the meson pair, the DD bar threshold, has a sigma u minus. So only those states will be allowed to decay, and the states which does not have sigma u minus, they will be forbidden. This has been recently confirmed by a lattice calculation of a 1 minus plus hybrid. So 1 minus plus in H1 multiplet here. And they found indeed non-zero decays to D star D bar and D star D bar star. They do not compute decays to DD bar, just DD bar, because the quantum number is not allowed. Okay, so in summary, Born-Oppenheimer EFT is a tool based on QCD, behavior of pentaquark and pentaquark potentials. This has to be confirmed by lattice, not as a new prediction based on the EFT picture, as I mentioned. I did not assume any specific color clustering as such. I mean, there is based on the short distance behavior or the long distance behavior, the potential captures all the color clustering what you want, and the dynamics is just given by Schrodinger equation. There are new results that I showed on the X38 TCC and pentaquark. So I just want to touch upon the future work, the slide. So extracting BOEFT potential is obviously a part of the problem. This is the core of our analysis. There are many states, as I mentioned, near threshold and states far away from the threshold. How do we understand this? Is finite number of adjoint hadrons or finite number of these light quark configurations needed to explain them? Then BOEFT predicts many states that have not been observed till now. Is there a reason? Do they have large widths or large decay rate? That has to be analyzed. So I just summarize what are the main questions, relevant questions regarding XYZ that has to be addressed. Some of the new states, for example, this G3900 resonance with quantum number 1 minus minus has been seen in E plus E minus collider by BESS3. It's a resonance state. They find it a large broad width. It is not 5 sigma till now, but they see it at around 3.5 to 4 sigma. The same is with this pentaquark state, PCC 4331 plus with preferred quantum number JP1 plus. The quantum number indicates, as I showed you, all the pentaquark had negative parity. This has positive parity, which means it's a p-wave state. Again, this state has been indicated at around 3.7 sigma. There are spectrum of other experimental states that we still have to study. States with strange mesons have to be included, and this has not been done. So this this has to be analyzed. In the case of isospin 1 case, there are these DC states, there are particular decay channels, and they have been connected with something like the light quark spin symmetry, which we have no idea about. It's just hypothesized to explain the decay patterns of these ZCZB states. And from our analysis, it seems there is a deep connection between this light quark spin symmetry hypothesized to the spectrum of the adjoint hadrons, isospin 1 adjoint hadrons. As I already mentioned, are there finite number of adjoint hadrons needed to explain this pattern of the states near or far away from the threshold? Some of these XYZ states discovery involve the pions specific. These are exclusive decays that we need to compute. So we need to include ultrasoft pions into our theory. That would meaning combining Born-Oppenheimer EFT with chiral perturbation theory. Spin potentials are the next part. The spin potentials we do not know the spin potentials. We are doing it first order perturbation theory. In the case of tetraquark, pentaquark, I use the spin splittings of the meson pair, but in reality, the spin potential should be again a function of R, something with short distance behavior and asymptotically matching onto the spin splittings in meson, antimeson, or meson baryon fashion. The spin splittings in meson baryon are constant. I mean, they are given by the expressions that I mentioned to you, whereas this spin splitting has to be a function of R. And then to accurately predict the spectrum, we need to account for this in the Schrodinger equation. I already give you brief picture that the mixing has to be understood because the states will mix. They are a superposition. One part is lattice QCD computation of these potentials and the non-perturbative correlator. There are states with all heavy quark has been seen for X6900 or dibaryons that was predicted by lattice calculations of TIFR group, Nilmani group. And something that I am currently understanding just beyond the spectra studies is doing finite temperature studies for XYZ in XYZ mesons, because X3872 was seen in heavy ion collisions. That would mean combining Born-Oppenheimer EFT with open quantum system and Lindblad equations and use Lindblad equations. And I am understanding, or I am trying to perform hydroproduction calculations, for example, for XYZ states, particularly X. So I'm learning that technique to do the hydroproduction calculations that will be extended for other XYZ exotics. These are relevant for experiments like LHC, and there's an upcoming facility in Germany, the pair facility as GSI, which will do the hydroproduction calculation. Even EIC aims to study pentaquark states. They do want to do it photoproduction. Photoproduction is quite difficult, but in the long-term aspects, obviously photoproduction needs to be addressed. Okay, there is a small thing here. I wanted to go into detail about hybrid critical missing, but I will just skip it. I mean, just outline how we will address it in the future work. Again, we perform the matching between NRQCD and Born-Oppenheimer EFT. But let me skip it. If somebody is interested, they can ask me and I'll come back. So this is a new aspect of, this is my last two slides. So a new aspect where I want to extend this method, Born-Oppenheimer EFT, or this multiple expansion that we use for heavy quark to systems outside of heavy quark. And the beautiful example is developing this potential non-relativistic general relativity theory to study gravitational atoms. Gravitational atoms are bound states of axion cloud around a rotating black hole. Axion clouds are trapped around the black hole due to gravity. Interestingly, if you compute gravitational fine structure constant here, I give the range of axion mass and stellar mass black holes, or axion mass and supermassive black holes. You do find that the alpha G is small. Alpha in some cases, the alpha G could be much smaller also, like about 0.01. And this is a multi-scale system where there's a hard scale, soft scale, and ultra soft scale, just like in the exotics that I showed you. Only difference is that in exotic there is this lambda QCD entering. There is no lambda QCD. And if alpha G is large, then this can mimic something like a lambda QCD system, or like the QCD system. So the potential non-relativistic general relativity theory would be an effective theory at the scale mu alpha G square. Mu alpha is the axion mass. There is a tower of EFTs that one needs to do. I already have axion EFT without gravity. We need to account for non-relativistic gravity or Newtonian gravity within axion EFT, and then integrate out the soft scale and arrive at this potential non-relativistic GR. Eventually, I believe that the potential non-relativistic GR will be useful to compute monochromatic gravitational waves. They will be detected, which will be detectable at advanced LIGO or Virgo experiments from axion transitions in the cloud, and also useful for computing Lamb shifts in these gravitational atoms, just like the Lamb shifts in the hydrogen atom. Extending this PNGR to study gravitational molecule, which will where the Born-Oppenheimer will enter into picture, that would be such something like binary black hole and axion cloud together, which will be the analog of hydrogen ion molecule into the system. And then you can study ionizations of the axion cloud that will emit gravitational waves to study the detection methods. So this is my final slide. So I end up with this thought that what is an XYZ meson? It is an elephant, and models are trying to address some part of the elephant where Born-Oppenheimer EFT will solve this problem in next five years at least. What is why our hope is we will pin down on the spectroscopy part, spectrum decay in next 5 to 10 years. So it's a good time to focus on hadron spectroscopy. Thank you.
Okay, thank you, Abhishek.
Yeah.
So any more questions?
Hi, Abhishek. So I didn't still understand when you do the matching. So you need the potentials in the Born-Oppenheimer theory.
Yeah.
So how do you get those? That's
I mean, so the potentials are either fitted. So this is the example of the potential that I maybe let me go to the pentaquark. So this is the example of potential that I use in my Schrodinger equation, which is obtained from the theory. Yes.
Mhm.
In the case of hybrid,
And
as I
sorry,
showed,
when you tell theory, how do you get this? So that's what my question is.
I mean, we know what is the potential at short distance is. It is given by octet plus some r square term. We know that the potential at long distance is given by the sum of sigma baryon plus the d meson mass, because it's a flat line. And so at intermediate distance, it can have any behavior you want. I mean, we just predict the intermediate behavior, but that needs to be confirmed by lattice. We have not done an analytic computation of the potential. We do the analytic compute. We know the behavior at short distance. We know the behavior at long distance. And
even
then
in
we
the
are
short
doing,
distance, I think the behavior is not completely known because there are 1 by m term, delta function terms, which are coming due to spin splitting, which
but
may
the
be
spin,
important.
the spins that I said, this is the first order calculation. The spin splitting is something that I definitely want to account in the next part of the calculation. I mean, already at the lowest order, even ignoring spin splitting is already a very hard problem to address. So just at lowest order, we ignore the spin splitting, we include the spin splittings as perturbation. But you are correct that definitely there are these 1 by m terms of spin splitting that has to be accounted for. It's a very good point. I mean, this is something that I want to address in the future problem. I'm not denying.
But in the long distance part also, you're assuming that these baryons, there are no interactions between them. You're just assuming they are free baryons.
Yeah, I mean, the interaction, I mean, what we are assuming is that the interaction between the baryon and the meson is happening through one pion exchange. So let me maybe just show you the example of the potential expression of the potential. If you just give me, yeah. So here is the potential expression, this equation 3, for example. At short distance, there is this octet potential plus adjoint meson mass plus some r square r4 term. At long distance, the baryons are interacting through one pion exchange here or two pion exchange. It does not matter, whatever you take, plus the energy at which these thresholds are. So we take all the threshold at 0, so this E1 is 0. So this is how we model the potential. I mean, in the hybrid case, the potentials have been computed by lattice, so we fit the hybrid potentials to the lattice computations. But in the case of tetraquark, pentaquark, it has not been computed. We know the short distance, we know the long distance part. And then we are just matching the short distance and long distance. This is the least we can do, I mean, at least at present. And then eventually when there is lattice data, then we will improve upon it.
Okay, thank you. Is there anybody in the online like to ask? Already left? No. Padmanath?
No, nothing from me.
Nothing. Okay, Shankar or anybody?
We don't have any questions.
Okay, if there is no more questions, let's thank Abhishek. Thank you.
Thank you for the
Thanks a lot.
opportunity.
Thank you.
I'll close. Thank you.
Okay, sure. Thank you. Thanks a lot.